Hello students, today I am going to discuss about volumetric strain due to single direct stress. Volumetric strain due to single direct stress. I told you about the volumetric strain in one of my lecture of strength of material, that volumetric strain is the ratio of change in volume to original volume. That is, if we are considering delta V is the change in volume and V is the original volume, then eta V, if we are considering the volumetric strain, then eta V equal to del V by V. So this is the volumetric strain. So for this, if I am considering a rectangular bar of length L, width B and thickness T, which is subjected to a direct stress P along its longitudinal stress, and the stress will be tensile in nature. So here I am considering a longitudinal bar which is having length L, thickness T and width B. Length L, this width B and thickness T. I am considering a bar which is having length L, width B and thickness T, and this bar of length L is subjected by a tensile force P at its both end, So and this force is tensile in nature. So in that condition, what will happen? Because of this tensile force along its length or in longitudinal direction, its length will change. If we stretch any body or any bar or any elastic body, its length will change because of this tensile force. So we are considering this change in length is delta L. This change in length is delta L. So in that condition, this stress will be a longitudinal stress. See, if we are applying any axial force or tensile force along the length or in longitudinal direction, there will be two type of strains. One strain is longitudinal and another strain is lateral. See, if we are applying a force along the longitudinal axis, its length will change. If we are considering delta L is the change in length and the original length is L, so the longitudinal strain will be, if we are denoting this longitudinal strain by eta, then it will be delta L by L. This is the longitudinal strain, or we can write it as P by E as per the Hooke's law. So this is the longitudinal strain and another lateral strain. This is longitudinal strain and lateral strain. This is the longitudinal strain and lateral strain. Lateral strain is change in, if we are applying force in longitudinal direction, length is changing as well as its width and the thickness is also changing. Here the length is increasing because of this tensile force in longitudinal direction, but its width and thickness will decrease because of this action. So this type of strain is generally called lateral strain. So we will consider the lateral strain as delta B is the change in width by original width or change in thickness by original thickness, or we can write it as per the Poisson's ratio. We can write it as lateral strain equal to lateral strain equal to mu into longitudinal strain, or we can write this longitudinal strain as eta. So this is the longitudinal strain and lateral strain. We have L length, B width and T thickness. So we can write here the volume of this rectangular bar will be L into B into T. And if we are considering delta L as the change in length, delta B is the change in width and delta T is change in thickness, so we can write here the V plus delta V, the final volume of this rectangular bar after applying this tensile force. So V plus delta V equal to L plus delta L. Why? Because the length, the original length, the length of the bar is L, and if we are applying force L, so its length is increasing. So L plus delta L, but the width is decreasing. So the original width of the bar is B, but it is decreasing. So the final width of this bar will be B minus delta B into thickness is also decreasing, so it is T minus delta T. So this is the final volume of this rectangular bar. If we further simplify this equation and we are taking common L, B, T from each bracket, then it will be L, B, T into 1 plus delta L by L into 1 minus delta B by B into 1 minus delta T by T. This is the equation, and if we further simplify this equation, we will have the final equation V plus delta V equal to, if we multiply all these brackets, then we will have LBT into 1 plus delta L by L minus delta B by B minus delta B by B into delta L by L. Now again minus delta T by T minus delta L by L into delta T by T. Now plus delta B by B into delta T by T plus delta B by B into delta T by T into delta L by L. This equation, after simplification of this equation, we will get this equation. This is the final equation. So if we ignore all the products of small quantities, so we will have the final equation V plus delta V. V plus delta V, V plus delta V equal to L B T 1 plus delta L by L minus delta B by B minus delta T by T. This is the equation we will get after eliminating all the small quantities. So this LBT is equal to V. This LBT is equal to V. This is the original volume of the bar. So here if we write V plus V into del L by L minus del B by B minus del T by T. So this will be cancelled. So we will have here delta V. We will have here this equation. This equation we get delta V by delta V equal to V into del L by L minus del B by B minus del T by T. This is the equation, and we can write it as delta V by V equal to this quantity, delta V by V. So this delta V by V is the volumetric strain. It is denoting the volumetric strain, and if we are denoting this volumetric strain by eta V, that is equivalent to delta L by L minus delta B by B minus delta T by T. See, this delta L by L is the longitudinal strain, and if we are denoting this longitudinal strain by eta 1, so this is eta 1 is the longitudinal strain, and the change in width by original width and change in thickness by original thickness is the lateral strain. And if we are denoting this lateral strain, this delta B by B by delta B by B is eta 2, and delta T by T is eta 3. So this is the equation, or we can write here eta 1 minus eta 2 plus eta 3 is the volumetric strain, or we can write it as eta x minus eta y plus eta z. The strain in x direction, strain in y direction, and strain in z direction. This is the longitudinal strain, and this is the lateral strain. And I told you in Poisson's ratio, the Poisson's ratio is the ratio of lateral strain by longitudinal strain. Lateral strain by longitudinal strain, and this longitudinal strain we are denoting by eta 1. So this will be the lateral strain is equal to, we can write here lateral strain equal to longitudinal strain we are denoting by eta 1 into mu. So we can write here in place of lateral strain, this is the lateral strain and this is the lateral strain. So we can write here eta V equal to eta 1 is the longitudinal strain minus eta 1 mu plus eta 1 mu. So this will be, if we take eta 1 as common, so this will be 1 minus 2 mu. So this is the equation for volumetric strain for a rectangular bar. Similarly, if we want to find out the volumetric strain due to single direct stress on a circular rod, see the previous case was for the rectangular bar. Now if we want to find out the volumetric strain for a circular bar or circular rod, so for that we are considering a circular rod of diameter D. The diameter of the bar is D, and the length of the bar we are considering L. And similarly we are applying a force P in longitudinal direction, or the nature of the force is tensile. Here the force is P if we are applying at the end of the rod. So if we apply this rod, if we apply this load in longitudinal direction linearly, in that condition the length of the bar will change. So if we are considering this change in length is delta L, so this delta L by L will be longitudinal strain because it is applying in, the force is applying in longitudinal direction. So we have the length of the bar and the diameter of the bar, so the original volume of this rod will be denoted by pi by 4 d square into L. This is the original volume of the bar when we are not applying force. After application of tensile force at the end, the length of the bar will change in longitudinal direction. So this delta L is the change in length and delta L by L will be longitudinal strain. And similarly, if the length of the bar will change, in that condition the diameter of the bar will also change. So if we are considering this diameter of the change in diameter of the bar is delta D. So this diameter of the bar is changing in lateral direction. So the strain produced by this change in diameter will be lateral strain. So here lateral strain will be delta D by D. Delta D by D will be a lateral strain here. So this was the original volume. After application of force, the final volume of the bar will be V plus delta V. V plus delta V is the final volume of the bar, that is equivalent to pi by 4. This is the original. This is L plus delta L. L plus delta L because the length of the bar is increasing. So here the quantity will be L plus delta L. Similarly, the diameter of the bar is decreasing. So in that condition, it will be D minus delta D square. The length of the bar is increasing and diameter of the bar is decreasing. So here is the final volume of this circular rod or circular bar. If we simplify this equation, we will have V plus delta V equal to pi by 4 L plus delta L into D square plus delta D square minus 2D delta D. If we further simplify this equation, we will have pi by 4 here L D square plus L delta D square minus 2 L D delta D. Now again plus D square delta L plus D square delta delta D square delta L delta D square delta L minus 2D delta D delta L. This is the final simplification of this equation. Now if we ignore all the product of small quantities, then we will have, if we ignore all the product of small quantities, so we will have the equation V plus delta V equal to pi by 4 L D square minus, this will eliminate, minus 2 L D delta D plus D square delta. This is the equation, this is the final equation we will get after eliminating all the small quantities. Now if we write here like this, pi by 4 L D square, this is equivalent to volume 2 minus 2 L D delta D plus D square delta L. So this is equivalent to V. So we can cancel out this V here. V pi by 4 L D square, this is V. Now here we have the equation for delta V. Now if we further simplify this equation, this will be pi by 4 we have pi by 4 d square delta L minus 2 L d delta d. If we take common d square L from this from this bracket, from this equation, if we take common as d square L, pi by 4, so here will be delta L by L minus 2 delta d by d. This equation we get if we are taking common as d square L. Okay, so this is equivalent to again V. So we, in place of this, we can write here V. We can write here V. So this is again equivalent to delta V by V. So this is the equation, delta V by V equal to this. So this delta V by V is the volumetric strain. So in place of delta V by V, we can write eta V. We are denoting volumetric strain by eta V. So if we write here eta V, I am removing this. So here eta V equal to delta V by V is eta V, and delta L by L is the longitudinal strain. Okay, so if we are denoting this longitudinal strain by eta 1, so this will be eta 1 minus 2 into delta D by D is the lateral strain. Lateral strain. The same concept we will apply here, the concept of Poisson's ratio. Poisson's ratio is the ratio of lateral strain to longitudinal strain. Lateral strain by longitudinal strain. So here if we put lateral strain equal to mu into longitudinal strain, and we are denoting this longitudinal strain by eta 1. So here we can write here lateral strain equal to mu into eta 1. So if we put this mu into eta 1 here, we will have the equation, that is eta V equal to eta 1 minus 2 mu eta 1. So here eta 1 minus 2 mu. Again, this is the volumetric strain, the equation of volumetric strain for circular bar. If we further simplify this equation, we will have pi by 4 L d square plus L delta d square minus 2 L d delta d. Again plus delta L d square plus delta L delta d square minus 2 d delta d delta L. This is the equation after simplification we get. Now if we eliminate or if we ignore all the product of small quantities, so in that condition we will have the final equation for V plus delta V is equal to pi by 4 this L d square plus L delta, this will eliminate, so we will have minus 2 L d delta d. Now again delta L plus delta L d square. This is the final equation. Pi by 4 d square L minus 2 L d delta d plus d square delta L. Now if we further simplify this, this will be pi by 4 L d square plus pi by 4 delta L d square minus 2 L d delta d. This is the further simplification. This is equivalent to volume of this circular bar. So in place of this we can put V. So this will be equivalent to volume of the circular bar. So this will cancel out. So here this is equivalent to delta V is equivalent to pi by 4 into this. So if we further simplify this, delta V equal to, if we take common d square L from this bracket, then if we take common pi by 4 d square L if we are taking common, then the rest of the equation will be d square L. So here d square L. So here delta L by L minus 2 again d square L. So here delta d by d. This is the equation. Now this is the lateral strain, this is the longitudinal strain and this is the lateral strain. I told you about the Poisson's ratio in the case of rectangular bar also. So here the lateral strain, longitudinal strain, if we are denoting by eta 1 and mu is the Poisson's ratio, so this is equivalent to lateral strain. This is equivalent to lateral strain. So if we put this eta 1 into mu in place of lateral strain, and in place of lateral strain if we put eta 1, in that condition we will have the equation delta V. This is equivalent to V. So we can write here delta V by V. This is equivalent to V. So we can write here V, and this is delta V by V is the volumetric strain. This is the eta 1 lateral strain minus 2 mu eta 1. See, this is the equation. Now again the volumetric strain for a circular rod, delta V by V, if we are denoting this by EV, in that condition the equation will be eta 1 into 1 minus 2 mu. This is the equation of volumetric strain due to single direct stress for circular bar. Thanks for watching the video and subscribe the channel for more lectures.